So your lab kit should contain, amongst other things, a couple of boxes such as this, and you should be able to pull a lens from in there, and it would tell you that this is a particular lens, and you should have 3 total of these. And so if you wouldn't mind, that's what's going to be the focus of today's lab. What we're going to do is a couple of different things. We're going to have some fun with the lenses today. We're going to try and figure out focal lengths. We're going to try and predict focal lengths. We're going to do strange things with the diverging lens and use it as a mirror. And then we're going to even nest things, 2 lenses together, and then separate them apart, look at the images and things like that. So it comes in a couple of different parts today. So if you look at the lab write-up, you'll notice that part 1 is to try and get an estimate of what the focal length of the lens is. And I would like to do this with both the converging lenses, which is to say ones that, if you look closely at the cross section of this, right, you can see it's kind of thicker in the middle, thinner at the 2 edges. That means it is a converging lens. This one is the diverging lens. You can kind of run your fingers in and out and notice that it's a lens which is thinner in the middle, thicker at the outsides. Okay, so we'll put this one aside for a few minutes, and we'll use the 2 converging lenses, and we'll grab ourselves a little bit of clay, which is going to be very useful. This little blob of clay here really is actually quite helpful. So when handling the lenses, highly recommend like a, well, you probably don't know what a CD is anymore, or a DVD. Well, grab it around the edges. That way you avoid putting your greasy fingerprints all over it and lousing up the images. Another way to do that is to take your little piece of clay and fashion a small handle out of it. And then you can pop that on there, and then you can hold this. Now that's going to be useful also because we are going to be putting these on a desk, and that will help keep it upright. Okay. So for more of an intro on some of these lab issues and things to go around, I've linked a video made by our former lab instructor John, and he has a great intro into using the clay, how to mount the lenses, how to measure stuff, and things like that. So for extra reference, please check his video out. It's also linked. But we will go ahead and get started here with part 1, which is to try and measure the focal length of both the converging lenses. So here I have a lens. I don't know its focal length, although it is marked on the box. So I have an idea of what it's supposed to be, but these are manufactured in bulk. Okay, they don't check them for any type of accuracy. They just go, we're going to make this, we're going to stamp that out, and we're going to say it's this. So nominally, that's what it should be. However, there will be great variations. And when I say great, I mean it could be, let's see, as much as a 0.5 centimeter for a 10 centimeter lens. So that's, what, 5% worth. I don't think they'll be off as much as a full centimeter, but nonetheless. Okay, so part 1 is essentially how to get the focal lengths of these lenses. First thing to do is, for the 100 millimeter lens, go ahead and see if you can get some overhead lights. All we want to do is hold the lens, and then I recommend something which has a bit of mass to it. A piece of paper isn't quite good enough by itself because it does let light in through the other side. So I have just a binder here that's white with a piece of paper on top of it. And if you notice, I'm just going to go back and forth, and you can see the image of my overhead lights coming up on the paper here. So what I want to do is get the best possible image I can on my screen here, which looks like it's going to be about, it's going to take a little bit of going back and forth to find this. And you'll just look for the sharpest possible one. And what I like to do is to start large with my variations in height, and then slowly get smaller and smaller. So I know it's right around there. Now all I got to do is measure it. So it would be great if I had a third hand, but since we don't, one thing that you can do is I used the measuring tape that was supplied with the lab kit. You can certainly try to hold it along with the lens. You can kind of prop it onto the clay here like this and hold that end here, and then go ahead and go down like that. Another way to do it was that it's a little bit harder, but if you have something like if you have the ability to build something that stands vertically on its own, that's great. I also tried to just put it on the wall. I put it on the wall back here. It's a little harder because then the image is a little tougher to catch on the screen and make sure that it's all focused. So nonetheless, it's pretty easy to get the image, and it's a little bit harder. So you might have a second person maybe doing this while you're holding the lens and they're just measuring or something like that. You can also put the book on the floor. I'm using my other hand here. If I put my screen down on the table here and I'm going to try and hold this, I'll put it up here so you can see. I'm going to try to hold this and measure. My hand is fortunately big enough to span the focal length of this, so I can keep the tape relatively straight. Do remember that here's a gotcha right here, right? This has centimeters on one side, inches on the other side. Make sure you're on the centimeter side. See how you go with it. Okay, so this is part one, basically trying to get a measurement of what you think the focal length of the both converging lenses. Actually, we're just using the 100 for this part of part one. Second part of part one, we'll go with the other one here. So that's, mine's looking about, do I want to say about 10? I do want to say it's close to 10 and a half. When you're doing this, please do make an estimate of your uncertainty, which is to say, try to estimate how much off you could be and in either direction, and change that into a range. Okay, so now you have what's called a confidence range or a confidence interval. So you'd say, oh, let's see here, my focal length is, well, and you're trying the best you can to measure to the middle of the lens, so there's a touch of uncertainty there as well. Yeah, gosh, I think I am pretty close. This is a touch over 10 centimeters. I'm looking at about, this is between 10 and 10 and a half. I'm almost thinking it might be closer to 10 and a half. So whatever your measurement is, make sure that you eyeball it a couple of times. If you are working in a group, please have everybody do all the measurement individually and try to do the best you can. Then feel free to take an average. Throughout the rest of the lab, please use the focal lengths that you've measured from this part one. All right, so we're going to say, well, okay, so I'm looking at maybe 10 and a half for the image of the lights. What does it mean to have something that's relatively far away? Well, it should be far away compared to the focal length of the lens. Now, if I go farther away, then will I get a different answer? So then the question is, if you've done this with the 10 centimeter lens, then get the 10 centimeter lens and your 20 centimeter lens. And here's my 20 centimeter. I think this is my 20. Yes, it is. Okay. And now what you're going to want to do for both of these is to try and get a much further away object. So maybe look out through a window and try to get a image focused on the screen from the lens, and then measure that distance. So this will involve, again, if you have someone there to help out, that's pretty useful. If not, then one easy thing to do is to for example, mount this, and you'll see this in John's video. Just mount this. The clay does kind of stick pretty well, and you'll be able to say, okay, I've got, you know, well, if you had it on a relatively good surface, you'd have that. You'd be able to hold this down with the clay on a table, right? And then you'd be able to say, you'd be able to mount this on a table and then have the tape measure close by, and then you'd be able to use a screen, and it'd be a lot easier instead of trying to hold everything. Nonetheless, in this lab, you're going to see me mostly holding things because I'm trying to get them into the camera view here. So, for example, if I look out the window here, and Zoom is going to auto-correct for the lack of light in here. It is actually pretty dark in here, but once again, I'm going to hold my binder up, and right, I'm going to say, okay, where is the image? Okay, and I can get a pretty good image, and if I look out the window, there's a couple of redwood trees that are pretty far away, so yeah, I can get, oh, that's pretty sharp right there. Yeah, I can get that to be pretty sharp. And so then once again, you're going to measure that distance. Light's going on. So we're going to measure that distance, okay? And do that with the 100 and the 200 millimeter lenses, both of the converging lenses. Okay, so that will be part one, and once again, try to consider your uncertainty, how far away either direction, just visually looking at the blurriness of the image, right? You're going to get the best in focus image that you can, and then you're going to move slightly and say, well, it's still kind of in focus, and then also take into account how well are you measuring from the center of the lens to the front of the screen, right? This type of thing. So in your uncertainties, try to consider all of those and make a reasonable estimate of what your uncertainty is such that you have a confidence range, because we will need that a little bit later in the lab. Alrighty, so that is part one of measuring the focal length. The first one is an estimate, and the second one with the two lenses is going to be fairly good if you can get an object which is far enough away. Alrighty, now we're going to move on to the diverging lens, and this is going to be a bit trickier, but we're going to use the lensmaker equation for this. Now, the lensmaker equation is the one that connects the radii of the surfaces of the lens to the focal length of the lens, right, by its index of refraction. So, once again, you can take the diverging lens, which is thicker. And also, the nice thing about this is you don't need the clay. This will actually stand up on its own on a table as long as it's flat, does not roll away. It will stay there. So it's much more difficult to try and measure the focal length of a diverging lens with the lens properties. In other words, if I try to say, oh, where's the image, and I'm looking back here, I know it's a virtual image, right? Now I'm going to have to try and measure the distance to that image, and there'll be quite a bit of uncertainty in it. So one other way to do it is, as we are going to do it, to use the radii of the surfaces and therefore use them as actually mirrored surfaces. Now, this is a tougher proposition because glass, being transparent, has a 96% transmission rate, more or less, through of the light from air into glass. It will have a 4% bounce back, though. So that 4% reflection, that's what we're looking for. This means that you're going to need a fairly dark area for this. And you're going to want something that maybe a small, like what I'm doing up here with the door, you're going to want a small bit of light coming in. If I shut the lights off here and I just look through that small bit of window up there, I can actually find where the image is from a reflection off this front surface. We're going to use it as if it's a mirror. It's a converging mirror, right? This surface is a converging mirror. So light incoming should bounce off and come to a focus. And as long as the incoming light is parallel incoming, then the image should be pretty close to the focal point of this mirror surface. But note that focal point is not the lens's focal point, it's the mirror's focal point. Okay? That means that the radius that made this, if you remember, is twice as far away as the focal point, right? That would have been where we put the needle of our compass in order to make a circle, which this is an arc of a circle, right? The shape of this lens. So by finding the focal length of this mirror surface, we'll double that and say that's the radius of this surface. Please do check both sides. Once again, these are bulk manufactured items. They do not check these for consistency or accuracy. So what's good on one side may not necessarily be 100% on the other side. Now, I think it'll be close, okay? It'll be pretty close, but nonetheless, they could be slightly off. So once you get the radius for 1 and 2, okay, what you want to do is put that into the lens maker equation. Now remember, when you're thinking about mirrors and lenses, not mirrors, but lenses for the lens maker equation, you're going to remember that there are signs to the radii, okay? So remember we call surface 1 the surface through which light first goes, and surface 2 is the surface through which light eventually exits, okay? If the radius is on the positive image side, then it's a positive radius, and if it's on the negative image side, it's a negative radius. That means that if this was a converging lens, like say, right, like this, I had light incoming from this side here, and then coming out through this side here, then what I would say is, this is surface number 1 on that side, this is surface number 2 on this side, and the radius that makes surface 1, because this is a converging lens, right? This surface looks like that radius is over here, and that's where I would expect the image to be real and positive. So I would call that first surface would have a positive radius. Naturally, this one would have a negative first radius because it's not over here, it's over here. Okay, that radius is going to be there, that radius is going to be there. All right, so make sure you get the appropriate signs on and then calculate what the focal length of this lens is. Okay, now, to calculate the focal length of the lens, the index I give you in the write-up, it's these are glass lenses, so we're going with 1.52 for the index of these. And if you want an extra challenge in this lab, maybe if you'd like a little extra credit, find a way to measure experimentally, to do an experiment and find what the what the index of refraction of the glass is here. It might be an interesting challenge. And it kind of dovetails with last week's lab. Alrighty, so we have hopefully the radii of these things. Now, this is listed as a 100 millimeter diverging lens, okay? Now, if I want to take and find out, well, is that really consistent with the other one? I've got my 100 millimeter converging lens and my 100 millimeter diverging lens. So in the lab, I said, predict the focal lengths of both of these using the lens maker equation. Well, that's not quite what we're going to do. You're going to predict it for the diverging lens using the lens maker equation, but we're not measuring the radii of this thing in the same way. What we are going to do is see if these two nest together. So if you nest these together, there should be no gap between the two. And if you try this with the 200 millimeter lens and put it on there, you'll notice there's going to be kind of a gap, right? And so what you're going to do is start looking through these things and saying, oh, is that basically like not looking through anything? Because if I have a diverging and converging lens of the exact same focal length, then the end result should be nothing, right? As long as they're nested fully together. Now, in order to check this, what you can do, there's a nifty little technique here. What you can do is start with them slightly separated, Okay, so suppose I'm looking at a faraway object out there. Okay, here comes the light. It's going to go through, say, the converging lens first, and then I'm going to leave a little bit of distance, and then it's going to go through the diverging lens. So with that optical system, what I do expect is that the converging lens is going to start converging the light. It's going to be converging, and then it's going to diverge. So I've given it a little bit of space to start converging, and then it's going to shift out, and then it's not going to be diverging, but it's going to diverge a little bit and then come back and converge, because I'm giving the rays a little extra distance to do the converging before I hit them with the diverging lens. Right? Now just take and maybe set up a screen over here, and then just take these things and start moving them slowly closer and closer together, and watch where the image goes. Okay? And you're going to have to move this forward and back in order to figure out how to get the image into focus. So what you should be finding is eventually, it's a kind of a limiting procedure. As you get these closer and closer and closer together, that image should be harder and harder and harder to catch on the screen. And ultimately, now I've got them nested fully together, and I look through them. I like to do this just to see if I can get what's the difference here? Am I getting anything here? And separate them slightly and see what happens. Yeah. So these should nest together. If they nest together reasonably well, both sides, right? Both surfaces like this, and nothing's happening, then we can say that the radii of curvature of the diverging lens should be the radius of curvature of the converging lens. And check and see if you would calculate the focal length of the converging lens, see if it fits in with your measurement of the focal length from part 1, right? See if it's falling within that confidence interval that you established for the faraway object. Okay. Alrighty, so now that's part 2. Okay, so we'll do that with the lens maker equation. Part 3 is now to actually set up an optical system. Okay, so I'm going to take my 20 centimeter lens. I'm going to mount it on a desk or on a table or something like that. I kind of recommend having it a little bit up so that so that you can catch it a little bit easier on the screen. But however, you'll find a great way to do this. You're going to put it down there, and then you're going to set up a object at about 2 times the focal length. So this is supposed to be, since you measured the focal length in part 1, this is supposed to be about a 20 centimeter lens. It probably isn't quite 20 centimeters, right? So maybe it was 19, or maybe it was 21 or something like that. Anyways, double your distance of the focal length and put an object there. I was thinking you could, as John did in his video, you can just take your cell phone, click the screen on, and in a dark room, again, right, you can just have this, you can have this here, and you can try and find where is that image. Now, if you have put it at double the focal length, then the image should be at double the focal length. Okay, so you're going to want to try and find, is the image the same distance away as the object? And if it's not, then go back and measure your focal length again. When it is, when you do find that distance to be just the same on this side as it is on this side, then you found double the focal length. Okay. Once you get to that point, what you should give it a try is to see if you can figure out how far away you should put an object such that you get an image that is magnified by twice and is inverted. In other words, the magnification is -2. Okay? First thing you're going to want to try and do for this, sketch out a ray diagram and use the thin lens with the magnification, okay? And solve for where the object is going to be, or solve, if you like, for where the image is going to be. And then go back and get the other one so that you can solve for where the object and image is going to be, okay? And then put your object there with the lens, and then see if you can actually measure what is the distance. Okay, so if you're understanding what I'm saying here, we're setting this up such that we want the image to be a magnification of -2. Draw it out, calculate where the image and object are going to be, then set it up and put the object in the image, or put the object where it's supposed to be, catch the image on a screen, and see if you have agreement. All right. You should be pretty close. I would say it would be good if you were within about 5% for this. I think that's pretty reasonable. All right, so that's the single lens. That was the 20 centimeter lens for part 3. Part 4, we're going to switch back to the 100 millimeter lens, again, the converging lens. And now what we'll do is we're going to, with a known object distance, okay, I tell you 30 centimeters in the lab, but with a known object distance, okay, where is the image? Catch that on a screen and then check it with the math, okay? Then take your other lens, the diverging one this time, okay? Take your diverging lens. Okay, I've got this set on the clay, say, or something like that on the table, and I have my object 30 centimeters away and light's incoming this way, hitting this lens and making an image. Now, I'm going to stick this diverging lens in the way, all right? And I'm going to put it 90 millimeters from this lens. So I'm going to put it right here. Okay, now, what's going to happen when the light comes through this one and then through this one? What I'd like you to give a try at doing is, as we talked about, this is likely going to be a situation where you're going to need to think about what is the sign of the object distance, okay, for lens 2. The image for this, right, I can find the image for this by itself without the second lens there, okay? I should be able to catch that on a screen. Now, when I have that on a screen, I'm thinking about this as my object for the second lens. Put the second lens in place, calculate what do you think the new image location is going to be. See if you can find it there, right? And compare those two. Pay attention to your signs, okay? And then take a look at the final image location and the final image's magnification. Calculate those two things and compare them with what you predict. Calculate those two things and then measure them and compare the experimental with the predicted values. Okay, so you're going to look at the image location of just the first lens. You're going to look at the image location from the final lens, right? After it's gone through both of them. You'll also, in between doing that, you'll calculate what the second lens's effect is going to be, given that you're using the image from the first lens to be the object for the second lens. Think about the magnifications involved. All right, you'll have an object way out here. You'll have an image. It'll be magnified a certain amount, bigger or minified or whatever it is. And then you're going to put this in the way, this lens in the way, and then you're going to look at what the final image looks like. Okay, compare the measured to the predicted, and that should be just about that. Don't forget to draw a ray diagram for that second lens, that second 2-lens system. All right, incoming, outgoing, and trace your rays. Alrighty, so that's the lab for this week. The due date is, since this is spring break, hopefully you'll have a little bit of time. If not, no worries. The usual due date is in effect. It is the Tuesday after we get back from break. So I'm giving you the time now. If you don't get to it until the weekend after spring break, great, no problems. Just please be sure to submit on Tuesday, which I think is the 9th or 8th, something like that. So, with that being said, I hope you enjoy a spring break. Play with your lenses, have some fun with them. They are good fun, and it does mess with your mind to think about what the light does as it goes through lenses. And next lab, we will start in on some of the wave experiments that we're going to do. Alrighty. So I wish you happy week off and some cheer and relaxation, and we will talk to you in about 10 days. Alrighty. See you then.